Welcome back, students, to our Chemistry 2620 video notes. In this chapter, we're going to be talking about the chemistry behind carbohydrates. So you've probably already seen carbohydrates in your biology classes, so you know that in general that carbohydrates are sugars, and these sugars are what our bodies need to sustain their normal processes. You know that plants make these carbohydrates using photosynthesis, and then our bodies take in carbohydrates and utilize them, and then we breathe out carbon dioxide as part of that greater cycle. So that's just our general reason that we're talking about carbohydrates, because they're important to actual life. And we're going to focus in first on monosaccharides. Monosaccharides are what people call simple sugars. When you look at simple sugars, they tend to be drawn as Fisher projections. The reason that they're drawn as Fisher projections is because this, according to chemists, not necessarily students, makes it easier to see all the chirality centers, because every point that you have a plus sign type drawing, right, where you see those lines cross each other here and here and here, those are all chiral centers. Whereas the carbons that are explicitly drawn out, like these other ones that I'm highlighting with a circle, these ones are not chiral. So generally, our carbohydrates are classified in two forms, aldose and ketose. So when we start looking at the difference, aldose should sound like, aldehyde, right? And to you, ketose should sound like ketone. So let's look at glucose. Do you see how in the glucose structure, there's this, an aldehyde? So glucose is a type of, or classified as, an aldose because it contains an aldehyde. Whereas fructose also has a carbonyl, but on either side of the carbonyl, there are two carbon groups, which makes this a ketone. So because there's a ketone present, we will classify fructose as a ketose. So ketose contains a ketone functional group. So in addition to this very generalized set of terms, we can also name carbohydrates. The name has three parts. The three parts to the name are the prefix, the parent, and then the suffix. So the prefix is either aldose or ketose. The parent tells you how many number of carbons there are in the chain, and the OSE suffix indicates carbohydrate. So, for example, glucose, because we already have the structure up there, we know contains an aldehyde, so we'd call this an ald. Oh, we leave off the SE. And then your glucose has 6 carbons, so we put in the hex, and then we add the OSE suffix. So glucose is an aldohexose. These names are wild. Fructose would have a ketone functional group, so we would start with keto. There are also 6 carbons in the chain, so we put in the hex, and then we end with the OSE. So fructose is ketohexose. So let's also look at L and D sugars. So when we look at these D and L sugars, one thing that I want to change here is kind of the order of which I've listed items here. So upon further research, what I've found is that the order of operations is different. And what I mean by that is originally Emil Fischer had said that the D and L configurations are really defined as the chirality center furthest away from the carbon group. Having an R configuration would be D, and having an S configuration would be L. So for example, let me draw that out. So if we look at, like, for example, L-alanine, L-alanine would have a structure where when the most oxidized carbon is on top, and right, the most oxidized carbon is the one with the most oxygen, so it's this one. When we look at this most oxidized carbon, the NH2 in this case would be on the left. And because the larger group here, right, being on the left, you know, the L and left, it kind of makes sense that maybe Emil Fischer would come up with L-alanine. Now, of course, he didn't use left, right? He used the Latin word for left, which just happens to also start with L. So when we look at the D-alanine, what ends up changing is the direction of that NH2. So now it's on the right-hand side. So this one is your D-alanine. So again, we're looking at the most oxidized carbon. When the most oxidized carbon is at the top, then we look to see where the chirality center is that's furthest away from the carbonyl group, while in alanine it's a pretty small chain, so it's just this chirality center here. And if your large group is on the left-hand side, that's your L. If your large group is on the right-hand side, that's your D. So this actually came first because this predates the RS system, which is like the Kahn-Ingold, and I can never remember the third person's name, system of assigning R and S. And so Emil Fischer was essentially coming up with a very straightforward way of assigning R and S to quickly illustrate that these two compounds with just the name are enantiomers of one another. So when you see D-alanine versus L-alanine, you know that you're talking about a pair of enantiomers. So then the other thing that Fischer did, so this came first, and then he was like, okay, well, I'm just gonna, I guess, take a guess. And he said that your D is going to end up rotating plane polarized light in the clockwise direction and your L in the counterclockwise direction. And so he guessed this. And it wasn't until the 1950s that it turned out that his guess was illustrated to be true. And so we really don't correlate our carbohydrates with D and L and the direction that they rotate plane polarized light, because things like solvent or the temperature that you run your polarization or polarimeter at can make a difference. And so, of course, we want to avoid properties that are dependent upon other things. And so we usually just use D and L here. And you might think, well, why in the world are we using this very old system? Why is it that we just don't update to R and S? Well, that's a really great question. So if we look at something like D-glucose, and remember glucose had like 6 carbons in it, that one, I looked up its name if we used R and S, and I'm going to read it to you. Are you ready? In parentheses, 2R, 3S, 4R, 5R, end parentheses, 2, 3, 4, 5, 6, pentahydroxyhexanal. That is what D-glucose would be. So you can see why in sugars we still continue to use the old mutation. So let's stop there for this video. We'll pick up in the next one with our cyclic monosaccharides.